Gravity fields. Let's talk about those. This movie with Sandra Bullock and George Clooney, I thought it was good. And there was some good physics in it too. There was a lot of kind of not so much real physics, but you know, pretty good, pretty entertaining. Think of a space, like look at the middle of the room. Imagine a cube of nothingness there. There's air there, so it's kind of fake, but is there gravity there in that space?
Yes.
How do we know?
By throwing an object through that space.
Okay, good. So if you throw something into it, gravity will pull it down, right? But does the gravity appear with the presence of the object, or is it there all the time?
It can change with the presence of the object.
The answer is we don't know. We don't know what's there until we put an object there, and then we know what's going to happen to that object. But we don't know what's there. And this was a bit of a spooky concept back in the day. Not just gravity, but magnetism and electric forces seemed to act over distances. And people didn't like that very much because it felt like witchcraft, right? And most people didn't understand science and stuff. And so there was a guy by the name of Michael Faraday who has a great story, and I'll tell it to you one day. But he wanted people to love science, and he wanted to help people learn. Because in those days there was a lot of charlatans, and there was a lot of sort of flat earther type people, and except they had an excuse because they really didn't know. And Faraday said, I need a name for these forces that act over distances. But I don't want to make it a scary name. I want to make it a nice, safe name. And so he called it a field. And a field was something that was really familiar to everybody. Everybody who farmed and everybody knew food comes from a field, and you know it's nice and grass and everything is nice. And so it's just a field, everybody. Don't worry. It's just a field. It's not, there's no witchcraft here. Don't burn me, please. And people liked it. And they went with it. And so we talk about gravity now as a field. And so this coffee mug has a gravitational field around it. Is the gravity bigger here or there?
The first place.
Right. Why?
Closer.
Because it's closer, right? What if so let's say I took a hammer and I put the hammer here. Could you calculate the gravitational force between these two?
Yes.
What would you need to know? Mass and
The distance between
and
the
the
centers.
distance. Good. And now you have the tools to calculate that force, right? What if I drop the hammer and I want to know just right here in this empty space, just right there, what will the force of gravity be on any object I put there?
You need to still know the mass of both objects that you want to do.
Okay, so I can't know the exact force, but can I know the force per kilogram of object I put there?
Yes.
Okay. So some of you are starting to click into this, and some of you are looking confused, and that's okay. I'm going to give you a different example, a bigger one. Here's the Earth. and we have a satellite out here. Can you calculate the force of gravity on the satellite? Between the satellite and the Earth?
Yes.
Let's say I want to put something out here in this place right here. But I don't know how heavy it's going to be. I don't know the mass of it yet. But I want to know the newtons per kilogram of thing I put there. That's what a gravitational field is. We actually don't know if there's gravity there or not until we put something there. But we know, because we've done it like trillions of times, we know what will happen to an object if we do put it there. And we can calculate the force per kilogram of thing we put there. This is called gravitational field strength. Right here, in this place, the gravitational field strength is known. Do you know what it is? You all know it. 9.8. Good. If I take a 1 kilogram mass, this is not 1 kilogram, but imagine it is. What will the force of gravity be on 1 kilogram?
1 newton.
No. Thomas?
6.967.
9.8 newtons. You take the mass, you multiply by 9.8, right? So the mass of 1 kilogram is going to be 9.8 newtons. What about 2 kilograms?
19.6.
Oh, good. Twice 9.8, right? And 3 kilograms would be so the gravitational field strength here is 9.8 newtons per kilogram of thing I put here. Does that make sense? So notice that this is equal to the acceleration of the gravity. Force due to the Earth will have some newtons per kilogram, and it will exert some acceleration, meters per second squared. That's the gravitational field strength of Earth at whatever place you put it. And I'll show you how to calculate it in a minute. Ever wonder why a hammer and a cup and a juice box and an elephant all accelerate at the same rate? Connor's like, no, I don't. Does everything accelerate at 9.8?
Yes.
No,
Everything.
gravity.
No, the force of gravity is different on everything, but its acceleration is the same.
The force of gravity is different, but the acceleration is the same. But imagine this. If I take a loaf of bread and a hammer and a cup and an elephant and a jumbo jet, and I hold them all up and I drop them, they're all going to accelerate at 9.8. Very different masses, but they all accelerate at 9.8. Now, what if I held up the moon? Because I can do that. And I let it go. Will it accelerate at 9.8?
Well,
Ainsley is shaking her head no.
Is it gravitational pull?
well,
Declan,
how
say
far
that
is it
again.
Is it gravitational pull between the two bodies?
So the moon is going to be pulled down, but also
pulled up?
the Earth will be pulled up. What if I hold up Jupiter
Then
and I release it?
And the Earth
then
gets
the Earth will be
Earth
pulled
gets eaten.
towards.
The Earth will be pulled up even faster than Jupiter is pulled down, yes? And so the acceleration between them will be fast, much faster than 9.8. The reason that a jumbo jet and an elephant and a loaf of bread all accelerate at the same rate is because all of those masses are negligible compared to the Earth's mass. If I drop a hammer, did the Earth move up?
No.
Yes,
Okay, yeah.
did. But it's so small we can't measure it.
Immeasurable.
Plus, there's a kid in Australia right now dropping hammers too, and so it balances it. I don't know the kid, but I'm assuming there's one somewhere. Let's go back. Okay, so space, empty place in space, there's a gravitational field there. And we can't calculate the exact force because we don't know what we're going to put there yet. But we can calculate the force per kilogram of object we place there. Okay. Now, if I place Jupiter right here, the Earth is also going to be pulled towards it. But that has nothing to do with the gravitational field strength coming from Earth. Okay, does that make sense? So this gravitational field strength in newtons per kilogram from Earth is the same on any object. And it does not take into account what's happening to the Earth. The Earth's going to get pulled too. And that may be a lot, or it may be negligible, or whatever. But we don't care about that. Okay. This one. So, Gravity. Sandra Bullock. Great movie. Maybe we'll watch one day. You're going to see this picture. I hate this picture. I don't like it. It gives you the wrong idea. But it's kind of fun to look at. There's this kind of net, and it makes like a little well, and the Earth sits in that little hole. I don't like it because it gives this idea that space is two-dimensional, and the Earth sits in this little hole and things just fall into the hole. Maybe it works and helps for some people to understand, but I think it creates more confusion than that. What shape, if the Earth's gravitational field had a shape, what do you think the shape would be?
Circle.
Sort of. What's a three-dimensional circle?
A sphere.
Yeah. I think you could draw that in concentric spheres going out. Because if you think about it, at a certain distance, the gravitational field strength of the Earth is going to be the same, right? It doesn't matter where on the Earth. If it's the same distance away, it's going to be the same gravitational strength. And then if you move out farther, it's less, and you move farther, it's less and less and less. Okay, anyways. Two bodies that are not in contact can exert a force on one another. This force can be gravitational, magnetic, or electrostatic. A force field. Force field. You learned about force fields today. When you go home and your parents say, "What did you do in school today?" Don't say nothing. Say, "I learned about force fields." Helpful way to describe the effects of such forces. Fields show areas of influence. So this is not things. It's not actual forces. It's a field. It's invisible. Can't see it. But we know it's going to act if we put something there. And we demonstrate, they allow us to predict the future is what they allow us to do. We know if we put something there, it'll have this many newtons of force per kilogram of thing we put there. Who likes s'mores?
Yee.
I love s'mores too. Think about a campfire. if you're wondering about this fields, I don't get this fields, it's weird. This is tinfoil hat stuff, these fields. Just think about a campfire. If I'm standing here, how hot am I?
Very hot.
Oh, I love it. It sounds like not very hot. Doesn't matter where you stand. Yeah, that's fair. If I'm here, I'm really warm, okay? And as I move away, what happens to my temperature? I'm getting colder and colder and colder and colder. Now, this is heat and not gravity, but it is a field, okay? And so you can imagine a field getting less and less and less concentrated. So if we put lines to that field, we could say that they kind of look like this. Does that make sense? Here the lines are close together, so you got a lot of heat. And out here the lines are further apart, so you have less heat. And the further you go, you have less and less and less heat. And it's the same with gravity or magnetism or electricity. Can't believe I just asked on video, how hot am I? It's great. This.
As long as you're not bothered.
I don't know him very well.
That's a good thing.
Yeah. G, a formula for G. So the force of gravity is defined as what? What's the formula for the force of gravity? No, not that one.
Oh,
The other one. It's back there.
Fg equals, big G mass times mass over R2, right?
Okay. So we have the simple version, and we also have the complex version, right? So for us here on Earth, G is 9.8, right? But we can calculate what little g is. You've been thinking of little g as the acceleration of gravity. It's also the gravitational field strength, 9.8 newtons per kilogram. So we can calculate that because if the force of gravity is, as Ashley said, gmm over r squared, then if we put that in for the force of gravity, what happens to these two m's?
They cancel out.
They cancel out, right? M over m is 1. And so little g is just equal to big G times the mass of the object creating the field. So mass of the object creating the field. And what's the R?
The radius between the two of them.
Good, this is the distance from the object. But because there's no other mass, we're not finding an actual force. We're just finding the newtons of force per kilogram of other mass that we would put there. And so the units can be newtons per kilogram, force per mass, or meters per second squared. It's also the acceleration that that object would experience due to the emanating object. Now if the two objects are similar, they'll accelerate at faster than that, right? Because they'll both be pulling each other. But if the object is like a satellite or something that has a negligible mass compared to like a big planet, it will accelerate at this unit as well. Does that make sense, kind of, sort of?
Yeah.
If it's a bit blurry, that's okay. Keep
Is this
thinking.
gonna be on the quiz?
No, this will be on your test next week.
On Friday?
The quiz on Friday is just Newton's laws.
The 3 new.
Yeah. So this is the first lesson
For
for the next one, and I apologize because it's so short and things are happening so fast, but I have no choice. I have to keep going. Okay. Mount Everest. We talked about Mount Everest this morning. This is like a great, it's all coming back. I love it when a plan comes together. We talked about climbing Mount Everest this morning. Really high. Mount Everest is at an altitude of 8,846 meters. Allegedly. Actually, there are some climbers that want to shorten it down. Did you know that? So, if you're a mountain climber, you have a love-hate relationship with Mount Everest. Like mother of all mountains, the Sherpas all love her. She's Mother Earth and everything. And it's like, it's the highest peak, so you have to love it, right? But relatively speaking, Everest is easy to climb. K2 is the second highest mountain on Earth. It's single-digit meters, I think. Don't quote me on that. But it's not very much shorter than Mount Everest. And there's like a single-digit number of people that have climbed it. It's so, and more people have died trying than have actually climbed it. And so climbers would love for K2 to be the highest peak on Earth. And they actually wanted to cut some snow off of the top, like make it shorter, but I don't think anyone's done it yet. Anyway, blah, blah, blah. Calculate the Earth's gravitational field strength at the top of Mount Everest. Go.
What's so hard about
I'm going to
K2?
give you 1 minute.
What's so hard about K2?
Ice, rock climbing, sheer faces, overhang.
You think you'll be a rock climber?
Maybe.
You believe in yourself, Joe?
Have I told you guys what I'm going to do when I hit 85?
You did 85.
Yeah, when I hit 85, I'm going to do cocaine and get in a squirrel suit and jump off a mountain. Not to die, like I want to try it. I want to do it now, but I feel the risk is way too high.
Yeah, it's like a stimulant for like.
No. Squirrel suits aren't needed either.
Why is squirrel
You know, the wings.
You should do it off the cheap.
You jump off and you fly. You know. I can't do it now. I have a family. It's too dangerous. But I want it.
Maybe email the class the day that I do that, and I'll come out and watch that.
Okay. Yeah, that'd be good. Have you guys ever seen McConkey? Watch this movie.
Is that a ski movie?
Sort of.
Oh, I've seen it.
Good, eh?
Really good.
So good. Just sad. Sad in a way, but really good. By the way, I don't do drugs. Don't do drugs. They're bad.
You'll just do them when you're 85.
When you're 85, I think it's actually a reasonable endeavor. Yeah, it's like, you know, the offset.
My plan is also harsh drugs, so minus the small harsh drugs.
Your plan is what? Harsh drugs when?
Minus harsh drugs, minus the small plastic. That is my
Oh boy, okay. Oh, like when you're old?
Yeah.
Okay. Okay. So, gravitational field strength, the formula for it is the part of the force, but there's no other m, right? There's no other object. So to calculate this, you go 6.67 times 10 to the negative 11 times the mass of the Earth, 5.97 times 10 to the negative, no, times 10 to the 24. Some people say 5.97, some people say 5.98, I don't know which is right. 6.38 times 10 to the 6 plus 88.4 46 meters. You have to add those all up and then square them. So the radius is a little bit higher than it is here on the ground.
That is just another.
Is my thing still filming? Am I still filming?
You had like 60.
Okay. What's the answer to this?
No. This is the radius.
Is it 9.8?
This is the Earth's mass.
Really?
Oh, I think that I'm. Oh,
Should be bigger than that.
hold on.
The radius fly.
I could be wrong.
Maybe we should have used 5.98.
6.653.
Let's do 5.98. It should be bigger than 9.81.
So 6.
I'll do
Hold
it.
on. Just let me just. So there's two formats.
Like literally add like that.
8, 8, 4, 6. You're multiplying. You said
Sing away, Sam. Sing away. What was that?
I don't know.
You got 9.8? I got 9.77.
Yeah, exactly. Yeah.
Well, that's not very good. I think it's supposed to be a little bit, oh no, that's right. Yeah, of course. It's 9.77, right? Okay.
This is a constant. This is just a number that always is forever. Which one? This.
Yeah.
This is the mass of the Earth. This is the radius of the Earth. Okay? So if you find something on the moon.
So why is Everest G 9.77 when here on the ground it's 9.81?
You're like super high. Yeah.
Why would this be less?
Because
Because you're higher up.
So you go higher up, the gravitational field strength of the Earth is less.
You have to add.
Go quick, go.
Acceleration using gravity and whoa, that's high up.
Isn't that the same thing as Earth's radius?
Yes, it is.
So it gets double?
Theoretically, that's just.
Oh, thanks, Connor. You got it, don't they?
That is just
It's okay. How long is it gone? Oh, it's coming up half. Stop it soon.
What's the mass of the satellite?
You don't need the mass, right? We don't know the mass of the satellite. So you're going to do G, little g, is gm over r squared. Now, there's a easy way to do this, and there's a hard way to do this. You can calculate it out and put in the 6.67 times 10 to the 11, and times the mass of Earth, 5.98 times 10 to the 24, and put in the radius, which you're going to have to add to the altitude. But what do you notice about this altitude?
Basically the same.
It's the same as the radius. So what are we doing to our distance?
You doubled it.
We're doubling it.
You just do 2.
So if we're doubling our distance, what's happening to our force of gravity?
It's it's quarter.
Good, Sam and Declan. It's 1/4 because 2 squared is 4, and then we flip it, right? It's inverse square rule. So
So it's 2 point.
if you calculate this all out, you'll find it's about.
2
Hold
point.
on, wait a minute. What's a quarter of 9.8?
2.5. 1 out. 2.4.
Well, close. Yeah, 2.4
2.35.
or something like that. So you could just do 9.81 divided by 4, and you get the same answer. You should.
2.45.
2.45.
Yeah.
I encourage you so it's quite a bit less gravity, right? And this is meters per second squared and or newtons per kilogram. So if you double your distance, you weigh a quarter of what you weigh here. Okay.
What's that? I don't know what's that. Don't mind me.
The moon.
I could drive there.
Yes, yes.
That's a lot more than you think.
That's an engine like.
No, it's not.
It's so long.
You could. Most cars wouldn't even make it that distance. 385,000 kilometers.
Wait, what about, don't they do that in like miles? Some cars?
So if you're going to put that into meters, 3.85 times 10 to the
10 to the 6.
no.
Oh, sorry, 5.
This is 5, but then we have to add 1,000 for the kilometers, right? So we want 8. So this is your distance. Let me ask you a question. Is the radius of the Earth going to matter in this case?
So what?
It's going to be fairly small. So it's kind of negligible. The radius of the Earth is much smaller than the distance from the moon to the Earth. So you don't really have to worry about the radius in this case. You can just use this as R. So let's find the Earth's gravitational field strength at the place where the moon is. So we're going to put in G and M over R squared. Love that. Love the
I
hiccup.
have the hiccup.
Can you hiccup right now? Hiccup. Go. Hiccup right now. Hiccup. Now you're cured. If you try to do it, it helps. So I'm going to do this over here. 6.67 times 10 to the negative 11, that's our constant, times the mass of the Earth, we'll go 5.98 this time, 24, over radius, which is going to be 3.85 times 10 to the 8 meters, and we have to square that.
Oh, because the Earth is the big one.
Do we need the mass of the moon?
No.
No. If we wanted to find the force on the moon, we'd have to multiply it by the mass of the moon. But to find the gravitational field strength in that place, we do not need the mass of the moon. What was it? Who's calculating it?
I am.
Good. Calculate away.
Oh, this is hurting my brain. 14.82.
Oh, that's a 7, probably.
That's a lot of numbers. 6. Oh, whoa, wait. 15.
When you calculate that, you should find that it's quite small.
It is
It's
quite-
0.0027 newtons per kilogram, or meters per second squared. It's really small. The Earth's gravitation is not much out there. And that's why it takes a month for the moon to get around the Earth. Because there's really not a lot of force pulling it towards the Earth. So it doesn't have to be going very fast to keep in orbit around the Earth.
It only moves 0.002 meters per second.
No, that's its gravity.
This is the acceleration towards the Earth.
Oh,
Its linear velocity is faster.
I see.
because there's a big distance around. But it doesn't need much velocity to keep from falling closer to the Earth. If that makes sense. We can calculate that too, but that's another lesson. Okay, so you can get the gravitational field strength of any object, if you know the mass, at any distance. You do not need the other mass. That's newtons per kilogram, so the force per kilogram of object you put in that spot. It's also the acceleration of gravity due to that object, meters per second squared.